Hello, everyone. Come on in. Anybody have any questions before we get started?
I actually have a question about the physics primer and the other homework that was a
Introduction.
duplicate on the mastering.
Right. Got you. Go ahead. I suspect I know what it is, but we'll see.
I was just wondering if you were aware that there was two of them and which one counts and how that's going to work.
Yeah, that's something I got to deal with. It's actually only one count, and only one has to be done. And since it made it erroneously two of them, what I have to do is I have to go through and take the highest score that each student got on one of them and put it in one particular column. And then I can't erase the other one, because if I do, then you can't go back and look at it for help, which I don't think you will, but still I wouldn't want to take that opportunity from you. So I'll have to change it to like imported assignments group instead of a homework group. And then I have to do the same thing for the other thing. So it's all something that I got to deal with, not something you guys got to deal with. Just know you only have to do one, and one physics primer and one introduction to mastering. And if you do that, I'll take care of the rest. Does that make sense?
Yeah, that makes sense. Am I the only one here right now?
No, there's four of you. Is this thing on? I'm actually a little bit in a kerfuffle here, because I went to hook up my iPad, and I noticed the battery was down to 13%. It had been left on since last time instead of powered down like I normally do. I don't know how I did that, but it's a special gift I have, I guess. So that meant it was pretty bad. And then I plugged it into, well, first I had to go get a cable, because iPhones and Apple changed their connectors, so they don't have the standard cable on it anymore. So I had to go get that, got that, plugged it into my USB multi-port thing, and everything was going great. And it said, oh, by the way, you can't connect this unless you update your software. And I said, well, this shouldn't take too long, so I'll go ahead and do that. This is like at 5:05 or so. And it started downloading, and I'm looking at this window, and it's like this long, and this itty bitty bit has been downloaded, and there's no stop download button. So I don't know how to stop it at all. So that's awesome. Hopefully it's not killing too much of our bandwidth. Are y'all hearing me pop in and out or anything? On my side, it looks good. And I normally get something saying unstable or something like that, or something about bandwidth. I'm not getting any messages, so I assume that's okay. But hopefully this all works. So how about any other questions? Anybody have any other questions about course or whatever? I don't think I put test 2, the practice test for test 2. I don't think I put that out yet. I should be doing that probably tomorrow. And I'll let y'all know when I do. And I probably just push the due dates back, because I think it might have been planned to be turned in on Sunday of this weekend, which would be like September 18th or something. I think I'm probably going to push it back at least till Wednesday, but I might even push it back to the following Sunday. We are a little bit behind, but not that behind. It's just a matter of, I don't care too much how late they get done. I just want to make sure you guys are ready to do pretty well on it, so that it's more of a learning experience for you than a frustration. Because really, at the end of the day, the tests that I care about, as you can tell from the syllabus, are the midterm and the final. So these are supposed to be getting you up to speed, so you know the subject very well, to take a comprehensive midterm, as opposed to just getting you up to speed to checking out work and stuff like that. So I don't want you looking up too terribly much. If you are, then that's an indicator that you need to buckle down and study a little bit more, maybe work some extra problems at the end of the chapter, the odds, have answers, work other problems, look at other problems being solved, that sort of thing. I was talking to a student today that was having some difficulties. So one thing I recommended to that student, and therefore I recommend to you guys, is I know a lot of students don't get to read their textbook at all. I understand that, and I wished it wasn't the case, and I wished you would learn to read better or be able to afford the time or whatever. But some of you just can't afford the time, or some of you just can't do it in a timely fashion. Like I was unable to do it in a timely fashion just because I read so slow, because I'm good at reading science, and that's the only way I can read to make sure I follow everything. So what I recommend you guys doing is at least go through the chapter before you start your homework, and read each of the examples. And if they say something that doesn't make any sense, then you can look back through the body of the text and try to find out the explanation of why they're doing that or something like that. But then go through, read all that, read the example and try to work the example through yourself. Then read the next example and try to work the example through yourself, and at least get all the examples done on the chapter before progressing to doing the homework of the chapter. And that's not as good as reading the text. You're not going to leave the class with this understanding of how physics affects the world, but you're at least going to get a leg up on being able to solve the physics problem. So give that a try. Yes, sir.
Mr. Actually, I have the exact same problem, and it's for people who have ebooks or who spend all that money for these online books or whatnot.
Right.
They actually implemented a audiobook feature, because I listen to audiobooks all the time,
Oh,
and
that's
so they
cool.
had an audiobook feature that goes along with the book. So that's the only way I can actually read through the chapters myself.
Is it through the web, or is it on their app, or both? Or do you know?
It's on. I only know about it on on Pearson.
Okay, gotcha. Cool. Yeah, that is helpful. If you can, if it actually is being read to you, the body of the text, you might get enough that it really matters, and that'll be fine. But then when you read the examples, you'll really need some time to sit down and look at it. But yeah, absolutely. If it's read to you, you'll get some of the background knowledge and stuff that's just, kind of unique to someone who's been through a college course. They'll know certain facts that are kind of interesting and helpful, and, conversation starters, that sort of thing. So yeah, absolutely. Thanks for that. Anybody else? All right. Well, we're going into a new chapter now, and the new chapter is on capacitance. I want to say it's chapter 24, and I'm going to pretend like that's what chapter it is, because I don't want to do anything other than find that out. But actually, I am getting ready to open up the text, and when I open up the text, we'll see whether it is or not. 21 was the Coulomb's law. 22 was Gauss's law. 23 was voltage. Yes, so 24 is capacitance. And this is kind of the weird thing about this textbook, is you actually study capacitance before you do resistance. So that's kind of a weird thing. But we're going to jump right in, and basically what I'm going to do is quite different from what your book does. I take and use Gauss's law every time I'm asked to calculate the capacitance, because this gives you yet another chance to study, to practice Gauss's law. So one of the capstone problems for this type of course is I give you a certain symmetric charge distribution. I tell you, use Gauss's law or use Coulomb's law, which requires, integration in Coulomb's law, or Gauss's law requires integration by fiat or something. And yours, I'll tell you to use that to compute the electric field. Then I'll say, calculate the voltage difference between one part and another of that capacitor. And then I'll say, all right, now that's using delta V equals negative integral E dot dl. And then I'll say, okay, now calculate the capacitance, which is gotten by dividing the charge by the voltage. So that's a very typical final exam problem, midterm problem, that sort of thing. Sorry about that. And that's the capstone problem. So that's why the way I work all these, I'm going to do 3 good examples. I will leave the 4th example to you to figure out. And hopefully that'll give you, again, some more experience with Gauss's law. Only now I'll do it much quicker, because I'm somewhat cocky and thinking that, having covered it for 2 chapters, you probably have a unique understanding and can at least follow me pretty well. if you can't, that's okay. Stop me anywhere you need to. But the main thing is we're trying to learn that. So here's the chapter 24. It's on capacitance. All these guys right here, anytime you see cylindrical shaped things and sometimes things that look like chiclets or certain types of gum that you put in your mouth, they're sort of padded and fatty. Those things are always capacitors. So all these are capacitors. All those little guys back there, they're actually resistors. You can see them with the bands on it. Some of them are, jumper wires in this case or something like that. But there's a lot of different things in a circuit. And just having this knowledge often can help you. I was telling my students yesterday that when I first got my job, I was in grad school and my advisor was acting kind of wonky. So I thought he might be leaving and I wasn't sure I was going to be able to finish my PhD under. So I started looking around for work just in case something like that happened. And I ended up getting hired by an engineering firm. Actually, it's a electrical/computer engineering company. We design integrated circuits, we design software to make integrated circuits. And I had to be, in that respect, somewhat of an electrical engineer, but mostly a computer engineer. And we would basically troubleshoot that software, make the software run for the customer's purposes and stuff like that. But it was a really good job, great money, full medical, dental, and vision insurance for me and all my family. And it was Blue Cross Blue Shield of California. I had stock options. I had a number in my head for salary, and they beat it by like 20%. For what I was going to take as a minimum. So I was like, yeah, I got it. It was a great thing. And they told me I could finish my PhD. They'd pay for it if I wanted to. It was just great. So immediately I had all this money. I went out and bought a HD TV. They were brand new. I bought one for like $5 or $6 grand, really expensive HD TV, which is funny because we still have it. And it works again per my correction, but it's really pretty pathetic compared to modern ones, which are really cheap now. You can get a modern one that looks way better and it's less than $500 for the same size. But anyways, it went out one day after 9/11, sometime after 9/11. So I had lost my job from this awesome place partly because of 9/11. And I called a guy and it was like $175 for him to come out and even look at it. It's going to charge me $75 an hour, and it's going to be a minimum of 1 hour. And then if he had to do any work and it took more than an hour, it's going to charge that plus parts. And then there's a surcharge on parts. And I was like, God, man, that's horrible. I was a school teacher at this time, a high school teacher. So I said, okay, well, never mind that. So I just opened up the back, made sure I unplugged it, opened up the back, and word of caution here, that is not enough. If you're going to go dilly dally with electronics, unplugging it is not enough, partly because of these capacitors. So I thought I had done everything good to ground it, but I looked and there was a capacitor just like those blue and light blue ones, and it was bigger, it had a silver top, it's got a little Mercedes symbol on top, but I looked and the little top had popped up, and that's a classic way that the capacitor shows you it's blown. So I looked, and lo and behold, it was the exact same capacitor I had in my toolbox. I cut out the capacitor. I soldered a new capacitor in. I might have accidentally hit a wire while touching a heat sink and welded my screwdriver to the heat sink because, again, I thought I had grounded everything really well. Now, that was enough to kill me, so just be careful if you try this. But lo and behold, for zero money, I was able to fix this thing, and it still works to this day. So this has been 12 years, and it's still working 12 years later. So a lot of the times when devices go out, it's almost always a capacitor. If it's some kind of electric motor or a TV or something like that. I got lucky, had the same thing happen with my chlorine generator for my salt water pool. Looked in there, the circuit board needed to be replaced according to the place. I looked at it, there was a capacitor blown. I looked up capacitor, cut it out, replaced it, works fine. Same thing with my HVAC unit. It was a startup capacitor for the motor. And actually, they're crazy. They put like 3 and 4 or 5 capacitors in one unit. So that was a little more complicated, but all that stuff's pretty good. So this is some of the stuff you can do as a result of having enough knowledge to be dangerous. Now, I don't recommend you opening up documents electronic devices like that, and unless you've had some experience with it or you have someone helping you. But definitely, if you ever even try it, make sure you go around with a grounded wire and touch everything after you've unplugged it to make sure you've touched everything with the grounded wire, not your hand. And that'll bring you a modicum of safety, but not necessarily all. So just be careful with that. So what is a capacitor? Capacitor, the classic sense, this is the diagram that it is in a circuit. It just looks like a battery. Notice how the battery's got a short side and a long side, except they're both the same size. So that's normally what they look like. Some of them are capacitors that only are allowed to be connected one way. So the positive's got to go to one side, the negative's got to go to the other side. If you reverse it, you're going to ruin it. If that's the case, they'll sometimes have a rounded side like this or an arrow across it. But either way, it's just basically two lines next to each other. That's the symbol. And the reason why that's the symbol is because this is the classic capacitor. It's two plates. One's positively charged by an amount Q. The other one's negatively charged by an amount Q. And there's either air or something else between them. In practice, there's never air unless you're doing one for demonstration. It's almost always some kind of an insulator in there. And what good physicists would use a perfectly cromulent word when they could use a word that sounds even more technical? So we don't call it insulator, we call it a dielectric. So they're dielectrics in between the metal. And you can probably see, given that diagram right there, a good reason for it. So it turns out, and we're going to show this in a second, that the capacitance increases with increasing surface area, so the surface area of the plate, and with decreasing distance of separation. So small separation and big area is what matters. Well, if that's the case, then you can see that's not an ideal capacitor, because ideally you want to make that area fit into as small an area as possible. So what they normally do is they'll roll it up like you see on the right there. And they'll literally make one side aluminum foil and the other side aluminum foil, and they'll just stick a sheet of vinyl or something in between it that's a dielectric, i.e. insulator, and they'll just roll it up as tight as can be. So that dielectric structurally gives it some soundness and keeps the thing from having the two edges touch each other, but it also makes it harder for quote unquote lightning to strike. We learned last lecture, or at least last chapter, that even air becomes a conductor when the voltage is 300 million volts, or excuse me, 3 million volts. Air can conduct lightning or electricity over a 1 meter distance. So when the electric field is up to 3 million volts per meter, then you're going to get a lightning strike. Well, the same thing happens with these little air gap capacitors, and the same thing happens with a dielectric in there, only the dielectric usually can take a larger voltage per meter, in other words a larger electric field, and they increase the capacitance by a factor by itself as well. We'll explain how that's the case, but that's the purpose of it. The capacitance formula, I don't like it in this way. I usually say C is equal to Q over V, and that's the way I remember it. So C, the capacitance, which is measured in something called farads, and 1 farad is defined to be 1 coulomb per volt. So you can see C equals Q over V is the equation. The reason for using them is basically they store energy. They do what a battery does, but they do so way quicker or way slower if you really wanted to. In other words, you can charge up a capacitor, and then you can deliver all its energy in an instant, or not exactly an instant, but in microseconds, for instance. Or you can slowly let it trickle out over hours if you really wanted to. So it's basically like a battery with a throttle, so you can tell how much charge you want to get out of it per unit time. And in that sense is really good. Plus it can handle recharging millions of times or hundreds of thousands of times, whereas a battery is going to die after probably hundreds, if not thousands at most. So it's just all around better in many ways. Of course, as a practical side, you should think, since capacitance is equal to charge per unit volt, you might think, well, what if I plot a charge on the vertical axis and voltage on the horizontal axis? Which one of these would have the highest capacitance? Well, if you go back and look at this, this is like Y equals MX plus B, but plus B is 0. That's why all of them are converging at the origin. So the author's given you a more or less an experimental technique to determine the capacitance of something. You just measure the charge on it for a given voltage, keep doing that over and over and over. And then you can see the M in Y equals MX plus 0 is clearly the C, because the V is the thing we plotted on the horizontal axis. So when they ask you which one of these is the highest capacitance, you guys would say
Hey,
Excellent. Yes. And again, I use the word guy for everybody. I apologize if that sounds offensive to anybody that doesn't consider themselves a guy. But anyways, that's just something I use. If it does bother you, email me and I'll try my best to stop. All right, so let me show you how to determine a capacitance. Now that I have that, your book actually does this in section 24 too. It starts determination of capacitance. So I'm going to do it as well. One thing I want you to do is realize that we did calculate the electric field for an infinitely large plate. We put these capacitor plates together really, really close so that in some sense, at least towards the middle of the capacitor, and if you have done your electric field mapping yet, you've seen that the electric field is pretty uniformly horizontal lines from the positive side to the negative side. And there might be a little bulging near the edges. That's your proof that the electric field is what we said it was, namely sigma over epsilon naught. I'm going to now redo that and show you how that is. So I'm going to stop sharing this screen and pray that my iPad will be able to be shared by air, since it's obviously not going to do it through my USB port. Okay, so I'm opening this up. I'm going here. See my Mac. All right, it works. Cool. Okay, so first off, I'm going to attack the idea of a infinite plane. So what I'm going to do is I'm going to imagine a coordinate system like such. Okay, that one wasn't too good. I don't like that one. Okay, and actually, I can extend that a little ways. I can extend that a little ways like this. Okay, so that works pretty good. Now, what I'm going to say is let's imagine a plate. It's a circular disc, say, centered on the origin. Something like that. Okay. Now, what I can do is I'm going to assume that it has, in fact, a surface charge sigma, and that the net charge, for instance, is Q, and it's uniformly distributed. That means that if I take a 1 millimeter by 1 millimeter square of it and find the charge on that, it's exactly the same as any other 1 millimeter by 1 millimeter square. So what that tells us is sigma is a constant. And it would equal, if I call this, for instance, okay, let's not do that. That was bad. And if I call this distance, for instance, R, then this would equal Q over pi R squared. Okay, so that's really what we're looking at here. Now, in order to do this, what I'm going to do is make use of my friend Gauss's law. And Gauss's law says the closed integral of E dot dA is equal to Q enclosed by that Gaussian surface over epsilon naught. So my Gaussian surface, I'm going to say, is a soup can whose central axis is along the z-axis and whose top is parallel to the plane and whose bottom is parallel to the plane. So it looks like that. Okay. And I'm going to make a hypothesis. My hypothesis is that E of Z, again, let's reiterate what I'm saying here. This is the x-axis, this is the y-axis, and this is the z-axis. So E of Z is going to be a piecewise function. It's going to be positive E of Z k hat for Z greater than 0 and negative E of Z k hat for Z less than 0. And that's by symmetry. There's no reason, since it's the same shape and all that stuff, there's no reason why the electric field should have a different Z dependence on the bottom than it does on the top. But we certainly expect it to point down on the bottom and up on the top. So there's my hypothesis. So I'm going to take, again, our major goal is to calculate C equals Q over V equals question mark. Okay, that's really what we're trying to calculate here. Obviously, to do that, I need V, but V is equal to the negative integral of E dot dl. And of course, in order to do that, I have to have E. So that's what I'm doing now, is calculating E. So the left-hand side of Gauss's law, LHS, is the closed integral E dot dl. Now, what I'm going to say for this structure is that there's going to be a dA here, and that's going to be dA k hat. There's going to be a dA here. I'll call this T, and this will be dA bottom. That's going to be negative dA k hat. And there's also going to be a dA SL for soup label, and that's going to be some dA n hat, and n hat only depends on X and Y. In other words, it has a I hat component and a J hat component, but has no K hat component. What it really is the R vector, or the R hat vector, in cylindrical coordinates. Okay, so just for the record, if you went by and studied the cylindrical coordinates that I pointed to you to on my YouTube channel, that's what that n hat would really be. So I have to integrate over all those surfaces. So this becomes the integral over the top, which would be, of course, E of Z k hat dot dA k hat, plus the integral over the bottom, which is negative E of Z k hat dotted with negative dA k hat, and then the integral over the soup label, which would be E of Z, and in this case it's actually plus or minus, because half of the plane is above, or half of this soup can is above the plane and the other half's below. So I'm going to put plus or minus there just to remind you that. And that's going to be k hat, and it's going to be dotted with dA n hat of X and Y. So hopefully you see from that, because the n hat dot k hat is going to be 0, the whole thing's going to be 0 there. Does everybody follow that? So what you see now, I'm assuming the silence was a good thing, is that all that's left is the first and second integrals, the one over the top, the one over the bottom. The dot product, like I said, is a linear operator, so I can pull that dA right out in front of the first K, and I have E of Z times dA. But notice we're on a set Z. We're on a Z that equals the distance from the origin to where that soup can top is. So even the E of Z is a constant, it comes out in front, and I get the integral of dA times k hat dot k hat, but k hat dot k hat's 1. The same thing happens with the bottom one, except it's got 2 negatives, but 2 negatives make a positive. So ultimately I get 2 E of Z times A for the left-hand side. Does everybody see how that worked? Anybody have any questions on that? Okay, so that's my left-hand side. Now I'm going to do my right-hand side, which is often the hardest part, but in this case, it's pretty straightforward. It's Q enclosed over epsilon naught. And Q enclosed, if I just call this area up here the same as I called it down there, which is just A, right? Then this will just be sigma times A. And the bottom, of course, is still epsilon naught. So does everybody agree that that is the right-hand side of Gauss's law? So I tried to show it as a different color so we know that was the end. So now I'm going to say left-hand side equals right-hand side. And I get 2E of Z A is equal to sigma A over epsilon naught. You can see immediately that the A's cancel out and I get E is equal to sigma over 2 epsilon naught. And I'll make it a piecewise function again. K hat for Z greater than 0 and negative sigma over 2 epsilon naught K hat for Z less than 0. Does that make sense to everyone? All right, so let's, thank you. Anybody have any questions before I go on to the next part? All right, so let's
Is
imagine.
it a constant value or is
Go
it
ahead.
dependent
Yes.
on
The constant
position?
value sigma?
Yeah, so it's not dependent on position. It won't get
No.
weaker.
No, this is supposed to be a uniformly distributed charge over basically a metal. So that's, metals naturally do a uniform distributed charge over the surface. So yeah, the sigma is supposed to be a constant. It's the total charge of the disk divided by power squared. And you see, as long as you're really close, in other words, Z is much, much less than R, then this has no Z dependence whatsoever. So I tell my students, this is why you often go into like classrooms and they'll have fluorescent lights, but then they'll have a plate over top of them that diffuses it, because that makes like a sheet of light as opposed to a rod of light or a ball of light. A ball of light is like a point charge, so the brightness falls as 1 over R squared. A rod of light, which is the fluorescent tubes, acts like a rod of charge, so the brightness falls off like 1 over R. But a plate of light has no Z dependence or no distance dependence whatsoever. So as big as you can make those diffusing plates to put over fluorescent tube lights, the more complete the light is. In other words, once you get halfway to the floor, it's barely going to be any darker than it was at a quarter of the way to the floor, that sort of thing. Okay. All right, now that we have, and that's just a neat little sidebar that helps you remember the dependence. That's why I do that, is we all remember that point charge is 1 over R squared. And that's also why, for instance, Einstein said when he was asked, Professor Einstein, do you believe in ESP and telekinesis? And this was right after he had discovered the general theory of relativity. And he said, well, if you show me it obeys a 1 over R squared law, then I'll believe it. So that's, that tells you that the 1 over R squared law is something fundamental, and it is. It's basically something I'll talk about when we get to magnetism. So, all right, now we got that. Now the next part is I got to calculate the electric field between 2 of these plates. So let's imagine a capacitor. And remember, a capacitor has a positive charge plate and a negative charge plate. So I'm going to say this right here and this right here. Okay, this one's going to have a charge of plus Q. This one's going to have a charge of minus Q. So what I want you to think is, let's make this side red for a reason that's about to come out obvious. So the electric field due to the red one, on the left-hand side of the red plate, which way does that electric field point?
To the left.
To the left. So I'm gonna put a red arrow there. What about between the plates? What way does that plate create an electric field pointing?
To the right.
Right. And what about on the other side of the plate, the negative Q plate?
To the left.
Still talking about the positive Q plate. To the right of the negative Q plate, wouldn't that still push to the right?
Wouldn't it go into the negative plate?
We're pretending like the negative plate's there. Excuse me, we're pretending like the negative plate's not there. So just by continuity, you know that if it points to the right next to it, it's going to point to the right over here as well. So we're pretending like negative q is not there for right now. Does that make sense?
Yes, I didn't know we were pretending that.
Yeah, that's my fault. Sorry about that. It's a play world. We're pretending. Okay, how about now? Forget about the positive q plate. Let's think about the negative q plate. Between the two plates, which way does the electric field due to negative q point?
Into the plate.
Exactly. So it points to the right. And I think you'd say that to the left of the positive q plate, if the positive q plate wasn't there, it would point to the right as well. Y'all agree with that?
Yes.
Okay. What about to the right of the negative q? Which way does it point?
To the left.
Yep. So you can see out here, the electric field is equal to 0. And out here, the electric field is equal to 0. But in the middle, notice they both have a magnitude of sigma over 2 epsilon naught. So in the middle, I think you can see that the electric field is sigma over epsilon naught, because that's sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So that's what the electric field is in the middle. Everybody see that now? All right. So any questions on that? Okay, so I'm going to assume that that makes some sense. Now what I'm going to do is I'm going to draw another coordinate system. Okay, this is going to be my x-axis. This is going to be my y-axis. And I'm going to imagine the positive q plate right here. And it's actually zoomed in. So this goes for essentially infinity this way and this way. In other words, we're so close that it's might as well be considered infinitely far away. And now I'm going to say the negative q plate is right here. And that's at, in fact, a distance d. Okay, and this is negative q. But again, this goes on for infinity this way and infinity this way. Okay, now the electric field in this case points this way, and we'll call it E, but we know it's sigma over epsilon naught. Okay, what I want to calculate, because the C equals Q over V, I need that V. I need the voltage between them. Okay, so what I know is delta V, which is V final minus V initial, is equal to the negative integral of E dot dl. Okay, now this is what we said was a line integral, and ideally you're wanting the positive value, but if you calculate it, it comes out negative, just drop the negative and use it. But it's really good practice for you to try to make it come out positive consistently. So that way you're learning more about how to do the line integrals and stuff like that. So I definitely recommend you doing that. Now, what I'm going to do is I got to remind you that when you do a line integral, you have to evaluate the integrand along the actual line. What we saw last time, though, is that E is a conservative field, so that the path you actually take is irrelevant, but you got to choose a path. So in principle, you're sort of trying to make sure you alter the integrand, the E and the DL, to represent some curve you're on. And then you've got to use either the DL vector or the range of integration to show the direction that you're integrating. So in this case, whether you go left or right, I need to either show that with my range of integration, or I need to show it with the direction of DL. whichever one I choose, the other one just has to go in the positive coordinate direction. So that's the key to doing line integrals and not getting, off by negatives and stuff like that. So in this case, it seems to me that you can all tell the voltage is highest at x equals 0. Do y'all see that as the case? Again, if you connected this capacitor to a battery, the positive charges would run from the positive side of the battery and hit that left-hand plate. And that would slowly build up a positive charge. Those positive charges would compel the positive charges in the negative plate to run away and return back to the battery. So yes, the left-hand plate is the positive voltage and therefore the highest. Okay. Now we know the electric field is going to be a constant. And I'll just call it E. I could call it sigma over epsilon naught. Actually, yeah, let's go ahead and call it sigma over epsilon naught. So it'll be sigma over epsilon naught, because sigma is the charge per unit area. And it's going to be pointing in the I hat direction in this case. See, I've made a new coordinate system. That's just fine. We're allowed to do that from one part of the problem to the other, as long as we're not, using something that's related. I'm going to use DL to show direction of integration. Okay, now I want delta V to be positive, so I need the higher voltage to be the end point. So I'm going to integrate. I will use green here. I'm going to integrate this way. Okay, so I'm using the DL to show the direction. What that means is delta V is going to be equal to negative integral sigma over epsilon naught I hat dotted with, now here's my DL. My DL has to point to the left because I'm using that to show which direction I'm going. So I'll say, whoa, I don't know what happened there. So I'll say parenthesis negative dx I hat. Okay, so that shows which direction we're going. Now, since I've chosen that, that means the range of integration has to just be chosen from low coordinate to high coordinate. So the low coordinate is 0 and the high coordinate is D. So you can see again, the dot product is a linear operator. So that means this negative dx can go right through the dot product and end up to the left of that I, and we'll get sigma, negative sigma over epsilon naught dx I hat dot I hat, but I hat dot I hat's 1, and the negative is going to combine with the other negative to make a positive. So I'm ultimately just going to get sigma over epsilon naught integral from 0 to D of dx. And that is, of course, sigma D over epsilon naught, which did come out positive. So we did that right. And in fact, I'm going to stick to the way I've been doing this and trying to write the final answers that we're using in a different color. So I'll say that. Okay. So now I can calculate C. C is just Q over V. Well, the charge for a given area of the capacitor is sigma A. So I'm going to write that as sigma A, and then the voltage, as we just calculated, was sigma D over epsilon naught. So you see that we ultimately get epsilon naught A over D. And that is the ultimate formula. The capacitance for a parallel plate capacitor is epsilon 0 A over D. Any questions on that? So that process is something I call like the capstone type assignment that you should be able to do. So you obviously should expect to see that a lot. And since there's really only 3 symmetries that Gauss's law works on, you're really going to expect it to happen a very specific way. It's either going to be a infinite plane, infinite line, or a sphere. And that's just the way it works. So what I'm going to do now is imagine a coaxial cable, an infinitely long coaxial cable. And this is actually just like an example in your book. And you can see that example if you want, but I'm going to explain it basically. So does anybody have any questions before I move on from this one?
So if it was a sphere, would we take the differences in the surface area to be the area? Or...
So remember, Gauss's law says that the electric flux escaping a closed surface is equal to the charge enclosed in that surface over epsilon naught. So when you do a sphere or even a inner cylinder in a coaxial cable, the only charge enclosed when you're calculating the electric field between them is the charge that's inside the middle part. So no, the only thing that matters is really just the charge that's inside the Gaussian surface. And I heard someone else trying to ask a question too. That might have been the same question they had, but go ahead and ask if you don't, why he's thinking of that answer.
No, actually I had a different question. Can you run through that, how you determine your, like the scope of your integration again?
Okay, yeah. So you're talking about on that last step where I calculated delta V?
Yes.
Okay, so delta V is always V final minus V initial. That's what that capital delta means. It's always final minus initial, whatever variable it follows, and it's equal to negative integral E dot dl. So the E, we know, points from the positive plate to the negative plate. So that's clearly to the X direction, the positive X direction in our coordinate system, in the new coordinate system that we made. So that's why I wrote E is equal to sigma over epsilon naught times I. Now, the other part, the dot DL, I chose to use, in this particular case, I chose to use that direction of that DL to show what direction I'm integrating in. So in that case, I had to integrate from small voltage to high voltage because I wanted the voltage to be positive, because you're not going to get a negative capacitance. So that's the goal, is you're trying to do that. And that's why I told you to try to always do that, but don't worry about it if you miss. So the direction of integration must be from right to left. So I made it DL is equal to negative DX I hat, meaning it's a differential element parallel to the x-axis, but pointing to the left. So that's why the negative's there and the I are there. Does that make sense?
Yeah, that makes perfect sense. I'm seeing where I got mixed up now.
Okay. And then the other thing is, once you've chosen what you're making the direction with, the other thing that you had that choice with has to go in increasing coordinate direction. So in the case of this, the range of integration went from 0 to D, even though I really integrated from D to 0. Okay. All right. So I'm
to get a positive V value, we're always going to go from low charge to high charge. Just like
that's
a positive
way of looking
force
at it,
value
yes.
is that we always go from low time to high time, right?
Yeah. Yeah. So that's it. You're going to go from low charge to high charge, because low charge is what the positive charges run to, and that is therefore low voltage. And high charge is what the positive charges run from, which is, again, that would be the positive side of the voltmeter or voltage supply, that sort of thing. Okay. Anybody else? All right. So what I'm going to do now is I'm going to draw in a different orientation than your book normally does, because I always like to make use of the coordinate systems we're familiar with. So I'm going to do a blue coordinate system. And it is a 3-dimensional coordinate system. Okay. And that's it. This is, of course, X, Y, and Z. And what I'm imagining is a coaxial cable. So the cable that comes from your satellite dish or your cable company to your TV. at some point, or maybe to your cable box, it's going to be coaxial. Then it might switch to HDMI or something like that. And the coaxial is that round cable. When you look at the end, it's got a little wire in the center that pokes out. It's got some white stuff around the outside of that wire. And then it's got like some aluminum foil looking stuff on the outside of the white, and then some screen looking stuff on the outside of that. That screen stuff is actually your outer cylinder, and that little wire in the center is your inner cylinder, and that white stuff is your dielectric. So that's really what we're looking at here. So what I'm going to do is I'm going to say, okay, I have that is going to be a cylindrical chunk of wire that actually goes on infinitely far. Okay. And again, it goes infinitely far. Oh, that was not good. But we're just going to be looking at a length L that I'm going to make use of. This, in fact, has a radius equal to, let's call this RA. And then outside of that is a concentric cylindrical shell like that. And the radius of this guy is going to be RB. Okay. Now, again, this goes on for infinity, but I'm going to call this length right here just plain L. Okay. What I want to calculate is C equals Q over V equals question mark. So this is the big problem. I have to, in order to do this, I got to calculate V. But V requires me to know E. So I've got to use Gauss's law. Luckily, because of symmetry, I can use Gauss's law. Let me fix that. It looks, I can make that look better. So I can use Gauss's law to calculate the electric field. I can then use delta V equals negative integral E dot dl. And then I can take Q and divide it by V, and that'll give me my capacitance. So I'm going to be calculating the voltage, say, from the inside to the outside. And what I'm going to do is I'm going to assume the inside has a charge of plus Q. And I'm going to assume the outside has a charge of minus Q. And what that really means is that it's uniformly distributed. They're conductors, so it's uniformly distributed such that lambda equals a constant, which equals Q over L. So in other words, I chose that Q because this specific L was taken. Okay. So we'll actually get the result in terms of lambda. That's the key thing I'm saying here. All right, now to do this, I need the electric field between the two cylinders, the cylinder in the center and the cylindrical shell on the outside. So my Gaussian surface has to be something that's the surface is literally perpendicular to the electric field, and therefore the differential area element on the surface has to be parallel to the electric field or perpendicular to it. So again, this is a case where we think of the soup can. I didn't use my cheating tool there, so it actually looks okay, but I'm still going to make it a little better like this. Okay. Then I'm going to draw another one straight down here, another one straight down here. This is my Gaussian surface. Okay. Okay, the radius of that now is going to be just plain R. Okay, but R is definitely less than RB. That's the main thing that you're seeing here. All right. So first off, I'm going to start with my solution. To do so, I'm going to make a hypothesis. And my hypothesis is that my electric field, E, is a function of cylindrical coordinate R, and that it points in the cylindrical coordinate R hat direction, that same N that I used in the last problem. Okay. Now I know that dA for the top is going to be dA K hat. That's for the top of the soup can. I know that dA for the bottom is going to be negative dA K hat. And I know that dA for the soup label is going to be dA R hat. Okay, now technically that dA, if you're really using cylindrical coordinates, that dA would be RD theta. That would be the left-right extent of the rectangle, and then DZ. So that would really be what dA is. But again, we're not really trying to do any integrals. In fact, we're trying to avoid integrals like the plague, but we're using the fact that an integral is really simple to do it. So now I can say the left-hand side of Gauss's law, closed integral E dot dl is equal to the integral over the top, which is going to be E of R hat dot dA K hat. Obviously, the dA can go through the dot product because it's a linear operator, and R hat dot K hat gives me 0. Plus, we're going to have the integral of E of R hat dotted with negative dA K hat for the bottom. But again, that R hat dot K hat is going to give me 0. And then plus the integral over the soup label is going to give me E of R hat dotted with dA R hat. But we're evaluating that at a specific R, the radius of the Gaussian surface. Okay, so that E of R is a constant there. So this side just becomes E of R times the integral of dA, because the R hat dot R hat is 1. So I just get E of R times, now the surface area is going to be 2 pi R. If you cut the soup label, that would be the length. And then the height would be L. So I'm going to call that 2 pi RL. Any questions on that? All right, right-hand side, Q enclosed over epsilon naught. Now, we basically decided that the charge period length is lambda, which is equal to Q over L. So I'm just going to call this, well, I'm just going to call this, since it's the final answer, lambda L over epsilon naught. So now I can say left-hand side equals right-hand side, gives me E of R times 2 pi RL is equal to lambda L over epsilon naught. And that gives me E, the vector, is equal to lambda over 2 pi epsilon naught R hat. So this is literally what I was just talking about when I was talking about the light provided from a fluorescent tube light. That's a linear distribution of light, and it falls off, the brightness of it falls off just like the electric field of it as 1 over R. So this is what I was referring to there. Any questions on how I got that one? Okay. So now I'm going to attempt to show, because now that I have E, I can use delta V equals the negative integral at E dot DL and integrate from RA to RB or from RB to RA. But I need to show you that endwise. So I'm going to redraw my thing as seen from above. So I'm going to draw a circle. And then I'm going to draw another circle inside of that. Okay. And of course, that little one is the radius RA and the big one is the radius RB. So what I can do to show that is I can say, this distance from here to here is 2 RA. And then I can say that, let's say this distance from here to here is 2 RB. Okay, so that makes some sense. And inside, of course, this is plus Q. So I'm going to put this in a different color just to look a little less offensive. This is plus Q and outside is minus Q. So I know, for instance, that delta V, which equals V final minus V initial, is negative integral of E dot DL. Okay. I want this to be positive, so I really need to integrate it from low voltage to high voltage. So which way am I going? Am I going from the outer to the inner or from the inner to the outer?
Outer to inner.
Exactly. So if I put a coordinate system on here, let's do a blue coordinate system. That's my y-axis. That's my x-axis. What I'm going to integrate from would be from here to here. That's my direction of integration. My electric field, on the other hand, points this way. Okay. So E, as we found, was lambda over 2 pi epsilon naught R hat. And I'm going to let my range of integration to dictate which way we go. So I'm going to say use range of integration to specify direction. So we're going to go from RB to RA. Okay. So that means the DL just has to be positive coordinate direction, which means DL is going to be dr R hat. Okay. So what I just did there by taking DL to be equal to DL R hat is I chose a path along the variable R equals a constant, basically. So, or excuse me, R varies, but theta and K and Z is a constant. So by choosing that DL, I've actually chosen that path in some way. So now I'm going to say delta V is equal to negative integral of lambda over 2 pi epsilon naught R dr, or excuse me, I don't want the dr yet. I'm going to say R hat dotted with dr R hat. Again, the dr, since the dot product is a linear operator, you can pull that dr through the dot, through the first R hat, and put it right after the integral. And what we're going to get then is r hat dot r hat is 1. Out front here, I'll get a negative lambda over 2 pi epsilon naught integral dr over r. And I'm going to integrate that, of course, from RB to RA. And when you do that, you get negative ln of, or excuse me, negative lambda over 2 pi epsilon naught times the natural log of RA over R, well, over RB. Notice that RA is smaller than RB. So the ln is going to be a negative number. So if I flip that, I can make this positive and everything will be positive. In fact, I did it correctly. That's the main thing. So now I'm going to switch to red because this is a final answer. Lambda over 2 pi epsilon naught ln RB over RA is equal to delta V. So now that I have the voltage, I could say C equals Q over V. The Q, in fact, was lambda times L, and the voltage we found was lambda over 2 pi epsilon naught ln RB over RA, which is inherently positive, so that's good. So this is telling us that C is equal to 2 pi epsilon naught divided by the natural log of RB over RA. And actually
missing an L.
Yeah, thank you. Times L. And I was just getting ready to point that out. And in fact, you normally solve it for C per L. And some coaxial cable will actually have it printed on the side. It'll say a certain number of microfarads per kilometer or something like that. If not, you can still look up the manufacturer, go to their website, and they'll have the specifications. They'll tell you what the capacitance is for that coaxial cable. But yeah, that's the ultimate result is 2 pi epsilon naught L over ln RB minus RA, or excuse me, ln RB over RA. Any questions on that? All right, we got 10 minutes and I got one more that I want to do. And the other one, of course, is actually one where I'm doing for a sphere. So I'm going to do a sphere with exactly the same configuration. Maybe I'll use a big R instead of a little r, but the sphere is going to have a sphere at the center with a charge of plus Q and a spherical shell centered on that same center with a charge of minus Q. And I'm going to calculate the capacitance. So let me draw a diagram. Again, no one had any questions on the other one before I move on?
I mean, I guess my only question would be, how is data transmitted through coaxial cable? And would it be more beneficial to have a higher or lower capacitance of coaxial cable?
So capacitance, one, misaligns the voltage with the current. So normally, if you're looking through just a battery and a resistance, if you take and run an AC current through that, you'll see that the current coming out of the battery is exactly in phase with the voltage coming out of the battery, and the same thing with the voltage and current going through the resistance. However, when you go through a capacitance, there's this rule called Eli the Iceman, and that means that the electromotive force leads the current in an inductor. That's what Eli means. And then the Iceman means the current leads the electromotive force, the voltage, in a capacitor. So the current will actually go 90 degrees ahead of the voltage through a capacitor. So it changes it like that. And in fact, you can get it such that if you match the inductance per unit length with the capacitance per unit length, you can get away where they actually are are exactly in phase, and you can get resonance and stuff like that. So really the importance isn't whether the capacitance is good or bad. Capacitance is like a resistance in that it steals some of your energy. So what you want to do is optimize it to steal the least amount of energy. And you do that by adjusting the radii of the inner wire versus the, that sort of screen woven aluminum wire on the outside. So yeah, it carries current one way through the center wire and then a other way through the outer shell. And that's the way it works. I know that's sort of hand wavy, but basically what I'm saying is the capacitance is just another parameter like resistance for a wire. It doesn't necessarily make the signal any better or any worse. It just weakens it over distance. So if you know the capacitance per unit length, you've got to make sure you try to minimize that, or you're going to have to boost the signal at every 3 kilometers or something like that. And that's pretty much what the cable company does. With the DirecTV and Dish Network, though, they're just coming from a satellite dish to the side of your house, at the side of your house, and then into your house. So the capacitance and inductance doesn't really matter too much for them. I mean, unless the house is huge. Does that help you?
Yes, I suppose so.
Yeah, it's a lot more to learn. Don't worry. Okay, so what I'm going to do now is I'm going to draw a coordinate system again. And it's a 3-dimensional coordinate system. Like that. Okay, I'm going to say this is X, this is Y, this is Z, but it really doesn't matter too terribly much. I'm going to put a red sphere in the middle. It's not going to let me move said red square, or red sphere, excuse me. So I'm going to draw another one. There you go, that's pretty good. Okay, that's the one that has the radius of RA. And then I'm going to draw another one. Oh, dang it. That was really bad. Making me angry. Did it again. Ugh. I hate that. Ugh. So let's see. I'm going to do first off a little bit there. That's at 3. 1, 2, 3. 1, 2, 3. You're just trying to make me be a jerk now. And then 1, 2, 3 like this. So now I can hopefully go. There you go. Close enough anyways. All right. So what I'm saying is this is R. I hate you. This is RB. And this is RA. Okay. I have a charge of plus Q inside and a charge of minus Q inside the spherical shell. Okay. Now, what I'd like to know again is C equals question mark. I do know that C is equal to Q over V. And I know that delta V is equal to the negative integral of E dot DL. And I know that the closed integral of E dot DL, or DA, excuse me, is equal to Q enclosed over epsilon naught. So that's my premises. I am going to make the hypothesis. So here's my solution. My hypothesis from what we know about point charges and spherical charges. Point charge or spherical charges act like point charges at their origin. So I'm going to assume that the electric field is given by E is equal to E of R hat, but this time it's the spherical coordinate R, not the cylindrical coordinate R. And I'm going to say, of course, that dA is equal to dA R hat everywhere. And I'm going to draw my Gaussian surface like this. And I'm going to be mad that I didn't hit the auto fix. There you go. And that radius is going to be R. Okay, it's just being a jerk now. Okay. So that radius is supposed to be R. So the left-hand side of Gauss's law, the closed integral E dot dl, or E dot dA, excuse me, I keep going to that, is equal to the integral of E of R hat dotted with dA R hat. Again, that's going to become E of R times the integral of dA, which is E of R times 4 pi R squared, because it's the area, surface area of a sphere. Okay. The right-hand side is actually super easy. We got about 2 minutes left. The right-hand side is super easy. That's going to be Q enclosed over epsilon naught, which is just positive Q over epsilon naught. So left-hand side equals right-hand side gives us E of R times 4 pi R squared is equal to Q over epsilon naught. So we get E is equal to Q over 4 pi epsilon naught R squared R hat, which is exactly what Coulomb's law told us. Okay, so there's our answer for the electric field. Now I'm going to integrate. So delta V equals VF minus V initial is equal to negative integral E dot dl. So I've got my E there. I'm going to use the dl again to indicate direction. So direction of integration implies dl is equal to negative dr R hat. And now the range goes from RA to RB. So delta V is equal to negative integral Q over 4 pi epsilon naught R squared R hat dotted with dr negative R hat. Okay, that negative cancels out with the other negative and gives me Q over 4 pi epsilon naught integral R hat dot R hat's just 1. So I get dr over R to the 2, and I'm integrating from RA to RB, or excuse me, big RA to big RB. Okay, now the integral of R to the negative 2 is negative R to the negative 1. So that's going to give me negative Q over 4 pi epsilon naught R, and that's evaluated from RB to RA. And of course, RB is the bigger number. So it'll be 1 over a big number minus 1 over a small number. That's going to become out negative. So ultimately, the negative times the negative is going to give a positive. So I can just flip the order and get rid of the negative. It'll be 4 pi epsilon naught, and it'll be 1 over RA minus 1 over RB. And you can see that is in fact positive. And you can even get a common denominator and say that Q times RA RB. Actually, let me not write it there. I can see already that's getting in the way. So I'm going to say equals Q over 4 pi epsilon naught RA RB. And then this will be over RB minus RA. Okay. So that is delta V. I'm going to box that so I know where that is. Actually, I'm going to erase part of it because I don't know why something hates me evidently. So C equals Q over V becomes Q over Q RA RB over 4 pi epsilon naught RB minus RA, which you can see the R's cancel out, and I ultimately get I don't know what I get. I get, oh, I actually had that upside down. Yeah, that's upside down. So I'll say delta V is actually equal to Q RB minus RA. I think y'all would have caught that if we weren't rushing so badly. And this would be over RA times RB. So that makes this whole thing become Q over Q RB minus RA over 4 pi epsilon naught RA RB. So it means C, notice the Q's cancel out. I get 4 pi epsilon naught times RA times RB over RB minus RA. And that's it. Okay. So that's the
Isn't
three
epsilon not in units of like newtons meters squared per coulomb squared or something like that?
Is the unit of C, you mean? Is that what you're asking?
Unit of epsilon naught.
Oh, epsilon. Yeah, epsilon naught. Let me show you right here. Epsilon naught normally has units of coulomb squared per Newton meter squared, but a Newton times a meter is a joule, and a joule per coulomb is a volt. So you can actually make that into a coulomb over a volt meter. And then that helps you, because when you realize that the unit for capacitance is the coulomb per volt, which is equal to 1 farad, you can then see how that 4 pi epsilon naught ends up working out. It turns out, of course, time's up now. I actually went over about 5 minutes. Of course, everybody's free to go. I will wait for the last person to leave, but I will explain to you that epsilon 0 is the permittivity of free space, which is really a measure of how easy it is to allow electricity to flow through, in this case, a vacuum. A vacuum and an air are pretty close. In fact, epsilon 0 is for a vacuum, but epsilon for air is 1.000006 times epsilon 0. So not really that big of a difference. When we actually put something in the capacitor other than air or a vacuum, we can replace that epsilon 0 with a K times epsilon 0, and that K is called the dielectric constant. Or we can replace the K times epsilon 0 with just an epsilon, which is the permittivity of that particular dielectric material. So we'll learn about that next time. I would like you to give the example that your book does, which is the 2 long parallel wires. It's example 24.4. Make sure you do that. That's really sort of the last thing for you to do, but you have to use basically the equation for the electric field due to infinite line charge. And then now you have 2 of them side by side parallel. So they have to add, but of course the distance in one case is X and the other one's D minus X. So just keep that in mind. And you should be able to follow the example that your book did. The rest of this, which is what we'll cover next time, will be how this acts in a circuit, how it acts when I add a dielectric, and all that good stuff. So anybody have any questions before I let you guys go? This will be posted in a couple minutes, but yes, sir.
I actually have a question about the exam. I've been having internet troubles for the last couple of days with the bad weather. Cox has been like in and out on my internet. I was wondering if I could get an extension on the test.
I thought I was the only one.
Was it test 1 that you missed?
Yes.
Yeah, test 1.
So I normally do, but it's a 10-point deduction. So I can give you that. I will look. If it looks like everybody missed, then if everybody did miss, then I'll give you the 10-point deduction. If everybody didn't miss, then if everybody did miss, I won't give you the 10-point deduction. But if some people got it done on time, then I'm going to have to give you the 10-point deduction. But it's not that big a deal because, as you can tell from our syllabus, the actual grade based on online tests is 1, I'm going to drop the lowest, and 2, it's a low percentage. It's like 10% or something like that. So it's really not that big a deal. It's more about you getting more practice. So yeah, I'll do that and open it back up for you. Those of you who wanted it, you probably already emailed me, but go ahead and email me just to remind me, and I'll do that. I'll probably set it tonight, and I'll give you a week from today to do that.
Okay, thank you.
Remember, you still get multiple attempts, so get as high a score as you can. I think I give you 3 attempts, and only your highest counts. So I'm going to deduct, 10 points from that. But you have a week, so that'll be basically Wednesday of next week. Excuse me, Tuesday of next week. Okay. Anybody else have any questions? Any other questions? It's cool with me. All right. Looks like that's it.